Ever felt like your Git commands are stuck in molasses, taking ages to clone, fetch, or even just check out a branch? You're not alone. Many developers secretly struggle with Git performance, often without realizing there are powerful, built-in solutions. When your Git repo grows, it doesn't just slow down your machine. It kills productivity, wastes precious developer time, and can even lead to frustrating merge conflicts. This isn't just an inconvenience. It's a drag on your entire development cycle. By the end of this video, you'll master advanced Git techniques like LFS, shallow clones, and configuration tweaks to make even the largest repositories feel snappy again. Go build something faster. The hidden cost of large repos. What's slowing you down? Okay, so you've got a repo that's getting chunky. What's the deal? Git is fundamentally designed for text files, not huge binaries. Every time you commit a large asset, Git stores a complete copy of that file's version in its object database. Over time, that adds up, creating a massive history that your local machine has to pull down and manage. Honestly, the biggest culprit I've seen is often developers committing things they shouldn't. Compiled artifacts, huge datasets, even full node underscore modules folders. It's like trying to move a house with a bicycle. Git tries its best, but it's just not built for that kind of payload. A hot take. If your .git folder is larger than your actual source code, you've probably got a problem. This isn't just about disk space. It's about the time Git spends traversing that history for every single operation. Fetching, cloning, even Git status can become painfully slow. Git LFS, the binary whisperer. Enter Git LFS, large file storage. This isn't some hack. It's an official Git extension designed to handle large files. Instead of storing the actual binary in your Git repo, LFS replaces it with a tiny pointer file. The actual large file gets stored on a separate LFS server, keeping your main Git repository lean and fast. To use it, you first install LFS, then tell Git which file types to track. For example, Git LFS track star.psd or star.zip. Once tracked, Git automatically handles the pointer creation and binary storage. When someone clones your repo, Git pulls the small pointer files, then LFS fetches the actual large files only when they're needed. It's magic, I tell you. Real talk, LFS is a lifesaver for game development, design assets, and large data science projects. We saw clone times drop from 20 minutes to under 30 seconds on one project after migrating. But here's a word of caution. If you're constantly changing large LFS files, remember that each change still uploads a new version to the LFS server. It's not a silver bullet for every large file problem, especially if you're versioning gigabytes of video every day. Shallow and partial clones. Get only what you need. Sometimes, you don't need the entire history of a project going back a decade. For CI/CD pipelines or quick local experiments, often just the latest commit is enough. That's where shallow clones come in. With Git clone, depth 1, you're telling Git, hey, just give me the most recent commit, none of the ancestors. This drastically reduces the amount of data transferred. But wait, there's a lesser known, even more powerful technique for really massive repos, partial clones. Introduced in Git 2.27, partial clones let you specify what objects to download, not just how much history. This is super useful for monorepos where you might only care about a specific subdirectory, or for repos with a mix of huge files and tiny code. Combined with sparse-checkout, partial clones allow you to literally only download the files you need for your current task. Imagine a massive repo with hundreds of microservices, but you only work on one. Why download the other 99? This is a game changer for developer onboarding and local iteration on huge projects. I genuinely think this is one of the most underrated Git features. Still with me? We've talked about why your Git repo might be slow and how LFS can rescue you from binary bloat. But here's where it gets really interesting. What if you don't even need the full history or all the files? We're about to unlock some seriously powerful techniques to make your clones fly. Optimizing your Git config and hooks. Beyond file strategies, your local Git configuration can have a huge impact. First up, core autocrolf. If you're mixing OS environments, setting this correctly prevents Git from constantly trying to convert line endings, which can be a silent performance killer, especially on large checkouts. Honestly, I've seen teams struggle for weeks with weird diffs because of this. Next, consider gc.auto and pack.window. Git's garbage collection, git gc, cleans up loose objects and packs them efficiently. gc.auto runs this automatically. For truly massive repos, you might want to adjust pack.window to use a larger window size during packing, which can make operations faster at the cost of more memory during the packing process. It's a classic memory for speed trade-off. Quick side note, client-side Git hooks are another great way to enforce best practices and prevent performance issues. A pre-commit hook could check for large files before they even hit LFS or ensure you're not committing secrets. This helps keep the repo clean upstream, reducing the need for heroic measures downstream. It's about prevention, not just cure. Server-side and network optimizations. Sometimes, the problem isn't your local machine. It's the network or the Git server itself. Ensure your Git server, whether it's GitHub, GitLab, or your own self-hosted solution, has ample resources, CPU, RAM, and fast I/O. For self-hosted solutions, optimizing Git daemon or your HTTP server configuration can make a huge difference. Think about caching at the server level too. Another factor is your network. High latency can kill Git operations, especially fetches and pushes with many small objects. Consider using a CDN for your LFS objects if your team is geographically distributed. Some devs swear by SSH over HTTPS for slightly better performance due to protocol overhead, but honestly, the difference is often negligible compared to a truly optimized server setup. For enterprise-level scale, you might even look into something like Git's Protocol v2 if your server supports it. It's more efficient, especially for sparse checkouts, and reduces the number of round trips. This is bleeding-edge stuff for most teams, but if you're hitting extreme bottlenecks, it's worth exploring with your Git hosting provider. Wild, right? When Git isn't enough, alternatives, and advanced strategies. Okay, so you've tried everything. LFS, shallow clones, config tweaks, server optimizations. Still slow? For truly gargantuan projects, especially those with massive binary assets and hundreds of developers, Git might simply not be the right tool. Systems like Perforce or Plastic SCM are purpose-built for huge binary assets and offer different approaches to versioning that might just be what you need. They're not cheap, but neither is developer frustration. Another advanced strategy for monorepos is using virtual file systems, like Microsoft's GVFS, now called VFS for Git. This essentially virtualizes your file system, only materializing the files Git needs right now. It's a complex setup, but for organizations with repos measured in terabytes and millions of files, it's the only way to keep Git usable. This is definitely not for small teams, but it shows what's possible. The key takeaway here is that Git is incredibly flexible, but it has its limits. Understanding those limits and knowing the tools and strategies to push past them is what separates a good developer from a great one. Don't just suffer through slow Git, optimize it. You've got the power now. Go build something amazing and do it fast. Let's recap. Large binaries are the primary cause of slow Git repos. Git LFS effectively handles large files by storing pointers in Git and binaries on a separate server. Shallow and partial clones significantly reduce initial clone and fetch times by limiting history and files downloaded. Local Git configurations and server-side optimizations also play a crucial role in performance. For extreme cases, specialized VCS or virtual file systems like VFS for Git might be necessary. The key takeaways: identify and track large binary files with Git LFS from the start. Use Git clone, depth1 4ci/cd, or when full history isn't required. Explore Git clone, filter, and Git sparse-checkout for massive monorepos. Tweak your .git config for core, .autocrolf, and gc.auto, and use client-side hooks. Ensure your Git hosting solution is adequately resourced and consider network latency. If you found this valuable, smash that like button and hit subscribe for more deep dives into developer tools. Drop a comment below with your biggest Git performance pain point or your favorite optimization trick.